problem statement is here. This research focusing on improving brain tumor characterizations using the automated detection and segmentation. And we wanted to find out that if the classification of type of the tumor, if it's glioma, meningina, pituitary, or LASEN, or some other tumors. And also, in addition to that, we explored the reinforcement learning for the dynamic pattern of the tumor segmentations. And the reinforcement learning I use a group relative policy optimization, GRPO, and proximal policy optimization, PPO. So here, my null hypothesis. I have 10 null hypotheses. These are the 6 beginning of, and then I have 4 others that they are pending because of the lack of the data. So here, we hypothesize that labeled ground truth and pre-labeled ground truth have the same labels, and the models perform equally in terms of F1 score. And my another hypothesis was that fine-tuned YOLO is the best available method for the object detection, and that YOLO combined with SAM yields the best segmentation results. In addition to that, I explored whether heterogeneity in ostis-driven cancer cells significantly impacts the performance of automated tumor segmentation. And also, I hypothesized that GRPO does not significantly reduce the false negative compared to standard deep learning models. And also, PPO does not provide statistically significant improvement in segmentation boundary precision. So, talking about GRPO and PPO. So, depending hypothesis is also it says that mostly for those genes that express higher and those genes that express lower during the mutations. So the focus is how the genes playing the role that mutation can cause the tumors to happen, because it could happen to the significant numbers of the mutations in the body. So that's the reason that it's focusing on expressions of the some genes. That this is also, there are lots of statistical works in that part that if you're interested in this project, I will share the research link with you. Please see it, and then for the more depth. So for the data of the MRI, I use the data from the public data, just the robot flows, and in those data, it's just different types of the tumors, glioma, meningina, pituitary, and some other tumors that we talk about it. And we account for both homogeneous tumors and heterogeneous tumors to ensure the robust model evaluations. And to maintain the balanced and effective training process, as we all know, the data is split. We always split the data into training, validation, and test. So these diverse data sets improve the model's robustness and generalization ability. So what are the methods and the model's approach and outcomes? Here, I use 2 different methods, object detection and segmentations. These methods, they use for the traditional deep learning. So because they're static. So I use the YOLO and detectron for tumor localization, and SAM and YOLO, SAM2 and YOLO 11 for the precise tumor boundaries declination for the segmentation refinement. And then I also use different statistical metrics and statistical testings like ANOVA, Turkey HST, and also statistical methods of F1, intersection over union, and HST, and various statistical testings that we were talking about, matrices that to evaluate the results. So this is how it happened. I have lots of thousands of these images. I specifically chose that one for the one that there were some of my images, deep learning failed. So that's the reason, it's one of them. Here we see that we did it for detectron, and then we did it with YOLO, and then we did it with fine-tuned YOLO. And they have a different calculations. Detectron couldn't just only shows one, but others they show heterogeneous tumors. and different types. That is very different with the ground truth tumors, that is only glioma. But segmentation here, YOLO plus SAM, that in my evaluation, it shows that it's the best segmentation, and fine-tune YOLO 11 is also best object detection. Here it fails. It doesn't show any tumor. So that's a problem. So that's the reason that here I use the output of object detection for the input for the segmentation. That's the reason it's YOLO plus SAM. And the output of object detection is that boundary box that goes to the input for the segmentation of the SAM. And here the output of the object detection is the point. They just put the point in the areas that they are suspicious about the tumors. And that's how the segmentation is detected and goes to that part. And then it gives us different confidence levels. That with this confidence levels, that tumors, and also intersection over union, that how much of the tumors is overlapped with the ground truth to find the intersection between them. So I did lots of testings here. So I'm just going very quick to these slides. To here I did a ANOVA test, and it gives me this, that it's the null hypothesis is rejected. So I wanted to evaluate my null hypothesis here, and then I put it for different groups for the detectron and fine tune, and then group them 2 by 2 to test my null hypothesis. And then here I did a Turkey HSD, that to see how much percentage when I group the different detectron or YOLO together, or fine-tune YOLO with detectron, how many percent is one outperforming the another one. So this is also for the null hypothesis that I did. Here is the bar for when I have all of the models, but and all of my images, but I didn't provide all of my images because it was a discussion that I did it in the last previous time, that I have multiple images, and then I combine F1 is still an intersection over union, but it shows that intersection.
Sorry, what's the difference between F1 and
IOU, intersection over union. There are two different matrices.
Oh.
They have two different formulas. So and this one, I tested my null hypothesis at the beginning, the null hypothesis that I mentioned at the beginning, that it summarizes our null hypothesis finding that segmentation ground truth have inconsistency affecting model performance, and object detection models show significant performance difference, with fine-tuned YOLO generally performing the best. And YOLO plus SAM does not significantly outperform other models. And tumor heterogeneity impacts segmentation accuracy. And we will, to address the problems of the here, the reason that, because these are discussed last time, the problem of this, that we see that a static deep learning method was not able to detect the tumor's location and the tumor's numbers. Nothing, it failed. Why this happened? So this is how the story is telling us. This is taking us to introducing to reinforcement learning for the segmentations. So the traditional segmentation models like YOLO plus SAM that we talk about it in the previous slides, it struggles with adaptability because they make one-time predictions without refinement. But reinforcement learning is introduced to overcome these challenges of the traditional deep learning. So RL, or reinforcement learning, it improves segmentation by learning from previous mistakes and making iterative updates. So this allows for the better adaptability and reinforcement over the time. So that's the reason that we introduced reinforcement learning here. And as we saw here before, that YOLO plus SAM rely on only one prediction and lack this ability. So our hope is reinforcement learning can help us to address this challenge. Here is the transition that we talk about it. We first go to the say that my null hypothesis shows that fine-tune YOLO is the best objection detection. My null hypothesis shows that YOLO plus SAM is the best segmentation. So we go from YOLO and to detect a tumor, and then YOLO plus SAM segments them, and then reinforcement learning dynamically improve the accuracy. So this overcomes the limitation of statistical segmentation by making continuous refinements. So we select a combination of object detection and segmentation models to optimize the tumor analysis. That is how the architecture of YOLO detector on a YOLO plus SAM and GRPO and PPO is going. So this slide explains how reinforcement learning refines tumor segmentations using the concepts of the state, action, policy, and environment in the iterative learning process. That the reason that I'm bringing this slide is because it's going to one of my findings about the problems of that image. So here the states represents the current segmentation mask, the tumor boundaries, and MRI slice feature at a given step. The environment consists of the MRI image and segmentation mask, providing context for evaluating the model's performance. The models take an action by expanding, contracting, or modifying the tumor's mask to improve accuracy. So, and then the policy here is the model's decisions making a strategy, guiding how it modifies the tumor's boundaries based on the learning process. Here is the formula for the reward function formula. So it's very interesting here because it's going back to, it's relating to my next slide. The reward function here, it determines the how reinforcement learning evaluate the segmentation improvement. So here it shows that a predicting mask closely, it really assigns the positive rewards when it's the positive rewards, when the IOU intersection over union, those.
To the reinforcement learning, did you try just retraining on new data? So you had one problematic image that you pointed out where it got the prediction.
Yeah, I have lots of problematic images. Yes, I didn't try it from scratch. I fine tune it.
Or rather, so your reinforcement learning, you just went straight to reinforcement learning without trying to. Were those images the problem images? Were they in your test set or were they in your training set?
They were in the test set.
Training?
Test set.
In the test set.
Mm-hmm.
So did you try putting them into? If you're going to do reinforcement learning, are you going to do reinforcement learning on those images as part of your training set then?
I did it on all.
So why not train it on all and try it that way first before you try a new method to train it on? Does that make sense?
So I did it in both ways. One time I did it on all of them, and then I found those problematic images.
So
and
even when they were in your training set, they still got the predictions wrong.
Exactly.
What about oversampling the problematic images? Oversampling the minority classes is a common way of dealing with that.
Sampling?
Oversampling. In other words, put it in your data. If you have a problematic image, put it in your train set twice. Make it learn from it twice.
Yeah, to increase the weights, and then use the weights to increase the weights. I did also that one. I did it to improve the fine tuning, especially for YOLO 11. I keep using the weights from another one and then train it again to improve it. But the problem is because it's static predictions, it's just predicting once. So that's the reason that even when I did it different times, it's still, this images was one of those images. I have multiple images, but during this short presentation.
But with reinforcement learning, you're going to eventually have to make a prediction. It's going to be one prediction.
Yeah,
but you're not going to keep running it until you get the right answer. You You're gonna run it
Yes.
some number of times, and then you can say done.
Yes, but the point is for the reinforcement learning, because it goes to the matrices of the recall or false negative rates, and also intersection over union and dice on those matrices. And when they are higher, they give it rank, they give it the punishment or rewards the system. So that's the reason that it's iterative. Of course, it's all have a prediction. But the point is, it's that one is the one-time prediction, but that one is working with the reward system that we're talking here, that gives us the point, and then it goes back to the learning process to improve the mistakes, and then make it another predictions. So the segmentation is improving over the time. So here, exactly the reinforcement learning here, GRPO and PPO works here for the Lambda 1 and Lambda 2 and Lambda 3 and Lambda 4. So it assigns the positive rewards when the intersection over union, and dice scores increases. So it means that the predicted mask, it closely, when it's getting increased, it means that predicted mask closely match with the ground truth. Those, they have a more overlapping with each other. And when it applies penalties for a higher false negative rates or a lower recall, it shows that the tumors are missed, like that sections that we saw, it didn't show. And for the boundary pixel errors, it measures misleading between predicted and actual tumor boundaries. Anyway, these two, FNR and BPE, they're working with the GRPO and PPO, that we're talking about it in the next slide, that how they balance each other for the reward at the step of the time. One of the interesting parts is about the reward system is the change of a state. So we have a current masking, and that one is keeps updated. Even during one predictions, it keeps updating. Here, GRPO, it ensures that no tumors are missed. So in the reward system, this is panelized with the lambda 3 FNR here. That is with GRPO. And when the tumor is not detected, PPO focuses on boundaries refinement and minimizes the boundary pixel errors. So this model, it gets the negative reward if the tumor boundaries are misaligned, if those bounding boxes that we found, their YOLO was found in those, even it's misaligned. So that is for the PPO, BPE. And the positive rewards comes from the, as we talk about, that higher intersection over union and dice scores. And it's just reinforcing the action that improves the segmentation quality. Here, in this image, is the reason that this one is related completely to the project that I'm working right now. So this process, we see that begins with the YOLO plus SAM, as you see here. It generates the initial segmentation states that we're talking about. Establishing the state, it includes the segmentation mask, tumor boundaries, and MRI features. So the policy here in the reinforcement learning then determines the next action, deciding whether to expand, contract, or adjust the mask. The updated mask from the new state that keeps updating is fed into the system for the further learning. So here the reward function comes to evaluate the segmentation performance using the intersection over union and dice scores. And they assign a positive reward for the improved tumor boundaries alignments, and it penalizes the false negative rates and boundary pixels. So GRPO is reducing missed tumor GRPO reduces the mass tumors by penalizing the high FNR, because when FNR, false negative rates is high, recall is getting low, and when recall is getting low, that means that there are lots of false negatives, and it's very life threatening. So that's the reason that GRPO is just reduces missed errors, and PPO optimizes boundary precision by minimizing the BPE that we talk here, BPE. So this is how the system works here. And also we have sometimes unlabeled data. It doesn't matter that all the data is labeled. When it's unlabeled data, YOLO plus SAM is creating the pseudo labels by training the previous one and then using that predicting for another training, and that's how it's creating the pseudo labels here. Here in this image, we see that exactly YOLO plus SAM, GRPO, and PPO is one of my findings related exactly to that image, the issue one. So the process here, again, starts with YOLO for the tumor localizations. It detects the tumor regions using the bounding box. But here, the YOLO, it lacks the pixel level segmentation. So these detections in YOLO serves as an initial state that is important, one of the fundamental parts of the reinforcement learning. So we use that state, initial state, feeding it into the YOLO plus SAM for the segmentation refinement. And at this stage, YOLO plus SAM generates the pseudo labels that we talk about it. And it creates the segmentation mask without iterative refinement. And then pass it to the GRPO for the false negative reductions or higher recall. GRPO expands the search regions to recover the missed tumors. Here, the missed tumors of YOLO plus SAM, it found it here. It ensures that no critical areas left undetected. And then reward function assigns the reward function that we shows the formula over there. Now it comes to and it assigns the penalties for the false negative rates and reward accurate the detections. So that's the reason it could detect those two tumors. Here that YOLO also founded boundaries about. And then PPO, here it takes over from the boundary refinement and ensures that segmented tumor masks are accurately adjusted. PPO optimizes the mask by adjusting the boundaries to maximize the intersection over union and dice scores that we talk about it, to minimize the boundary pixel BPE, because it works with the BPE. And this process directly relates to a state action policy framework, that we talk about it here. And we talk about it here. That is a fundamental part of the reinforcement learning, that exactly in this process. So it keeps adding the ST plus one, that state plus ST plus one is a change of a state. So it keeps updating. So it involves the reward-based learning to reinforce the correct refinement and penalize the missed tumors. So after that, YOLO plus SAM improves segmentation but remaining static. GRPO and PPO outperforms by iterative refining mask. In this part, I did again statistical evaluations. So performance improvement of GRPO in the objection detection and segmentation. And GRPO reduces the false negative rates here from 15 to 5%, as you see here. So, and then the p-value is statistically significant. So, meaning that when it's statistically significant, it means it recovers most missed tumors. But precision drops slightly, and for other parts is not statistically significant, only for the false negative rates. And here is about PPO objection detection and segmentations. Also, we see that IOU and DICE scores and HD, those matrices are statistically significant. So the overall here, all of these comparisons, it shows that the this supports the previous slides that we talked about it, that GRPO enhances recall by detecting more tumors. PPO optimizes segmentation quality through boundary refinement. If you look at all of those false negative rates, precision, bounding box, IUU, and then also look at the GRPO and PPO values, we see that it's confirming what we talk about it and what the image shows us. And then here I did another statistical test, Turkey HC, that it shows the fine-tuned YOLO remains the best for the detection accuracy. GRPO and PPO also it shows significantly reduces false negative rates by reinforcement learning of prioritizing recall and segmentation quality over pure detection performance. And here I did Turkey HSD again for the segmentations. And this result also validates fine-tuned YOLO as the most reliable detection models, making the best candidate for the further segmentation and refinement. And these are the null hypotheses, the 6 null hypotheses that I had before and I presented before. This slide presents Turkey HSD comparisons for the segmentation performance aligning with the previous slide. And the GRPO and PPO significantly improve intersection over union, those matrices, compared to the fine-tuned YOLO and YOLO plus SAM. And you see that YOLO is 70%, GRPO is 78, PPO 76, and the p-value is statistically significant. It confirmed that how reinforcement learning enhances segmentation accuracy. There is no significant difference in intersection over union between GRPO and PPO. It just shows that both models perform similarly in the segmentation coverage. And for the DICE scores, another metrics, GRPO and PPO are almost also the same. Those supports that GRPO reduces false negative rates, but PPO refines segmentation boundaries. So these results, it all shows the role of GRPO, PPO in boundary refinement, and GRPO's role is in recalling the optimization, improving the recall, and for the PPO is mostly working on the boundary refinement. But there are also some pending hypotheses. For that hypothesis that I mentioned, still I have a lack of the 2D images, that it goes to the one region of the 3D images. But another issue that I have is the lack of the genetic data paired with my MRI data. So it relates to the gene expression and tumor segmentations, that it's aligning with the reinforcement learning, segmentation accuracy, and multimodal analysis. So a hypothesis 7 to hypothesis 10 it shows that when gene expressions significantly differ across tumor types, and it shows that if the gene expression biomarkers correlates with segmentation performance, or it shows that examine whether high genes like SOX2 and other NOG expression affect segmentations difficulties. And these are all I put it, this hypothesis remain TBD, as you see here, or inconclusive because of the data limitations. So it's a challenge in linking MRI and gene expressions and necessary of multimodal data integration for improved segmentation accuracy. Thank you for listening to this presentation. And if you're interested in this presentation, this is my research link. So I put all the steps of my work. It just doesn't go to that one, the last one. Yeah, all steps here in this research. So I put it one by one, and also for the gene expression part, that's how it goes. So please take a look if you're interested in. And also, please, if possible, please share it with other researchers. Contributions is very important in this research, especially for the lab collaborations, not the original collaboration is because of the lacking of this type of data. Yes, please.
Is this research that you're doing by yourself?
Yes.
Have you thought of, I don't know, grants or anything related to this? This seems to be quite a complex task that you have been building.
Yes, I am thinking about having a collaboration with some research laboratories and then apply for them grants. When there is a next generation sequencing, and when they're taking a DNAs from the bloods and those types, there are lots of devices that is not, those devices are not available anywhere. They just need lots of technologies and facilities.
I have to cut the questions short a little bit because we have one more speaker I'd like to get to. Thank you, though.
Thank you.
Is Trevon ready? Okay. And we think the share is going to work. Thank you, Fae.
Thank you.
I didn't give Fae a proper introduction, so Fae spoke to us about language models and langchain and graphchain. And now this is Trevon Babcock again, going to talk to us about Python's fundamental data structures. So hopefully things come up. And the live stream seems to be working again. So Hobson, yours wasn't captured, but I captured it locally, so hopefully I can upload it later.
Thanks.
Okay, can you hear me?
All right.
Yeah.
Can you hear me?
Yes.
Yeah.
Great. Well, I'll go ahead and get started. I'm Trevon, and I was introduced earlier, so I'll go for it here. Thanks for having me, guys. And so I'll be presenting the Python Basic Data Structures Quick Guide, which you see here, a table to help you compare basic built-in data type behavior characteristics when you're designing a program and working with data. So, okay, let's see. A data structure is a way of organizing and storing data to facilitate data access and modification. Data structures are also known as data types or just types or objects. They are the fundamental building blocks of the programs we create and maintain. We'll focus on lists, tuples, dictionaries, sets, and strings. Let's see. These are simple types, aka primitives, scalar types, or singular value types, which includes single string Unicode characters. Mutable means an object can change, elements can be modified, added, or removed. These highlighted are immutable. They cannot change once created. Immutable and hashable are related. Oh, wait, I went to one too far. One too far, sorry, guys. Okay, so immutable and hashable are related. Hashable means an object's hash value does not change over its lifetime. An object has to be immutable to be hashable. Hashable converts an input to a fixed size numerical value, a hash value, indicating the index where the data is stored, which makes lookups, insertions, deletions, and membership testing fast and efficient. How do you determine if an object is hashable? You use the hash function. Immutable hashable types include the simple types, dictionary keys, frozen sets, strings, and tuples, if all the elements are mutable. Okay, so let's see. Value types, ordered, duplicate, and indexing refer to the individual elements inside the data structure. So set elements, for example, must be hashable. They'll be in any order, no duplicates, nor can values be accessed by slicing or index, like sequences. Okay, so set elements, for example, oh, let's see, I already said that, I think. So let me skip here. Sorry, guys. Okay, so data types can be truthy or falsy. Truthy values evaluate to true or not falsy. Data types can be empty or zero, and falsy, as is the none type. Everything else behaves truthy. Okay. Yeah, sorry guys. Okay, so we'll talk about that or I'll address that. Okay, so lists. A list is a variable length ordered sequence of comma separated immutable values of any type enclosed in brackets. So let's see. Lists are our most versatile data type. So there are many ways to create lists using explicit values, comprehensions, concatenation, and repetition. We can also use the list function, which takes iterators, sequences, collections, and generators. The list function is mostly used to convert existing data into a list. Here, list A has various data types and duplicates. Let's add a tuple. Lists are not hashable. We get a type error. Let's see. List use cases, converting data when data needs to be modified frequently, and storing duplicates. Tuples. A tuple is an immutable sequence of comma separated values of any type. Parentheses are optional, but some situations require them. For me, tuples are more readable with parentheses. So let's go down here. They are very similar to lists. Let's create a tuple. Single item tuples must have a trailing comma. The tuple function can construct tuples or convert iterators, sequences, collections, and generators into tuples. Let's convert a string to a tuple. Tuples are immutable. Tuple A here includes a list. We try to modify the second element and we get a type error. However, if a value is mutable, you can manipulate it in its slot. Here we append a value to our list inside the tuple. So a tuple is not mutable, but it can contain mutable objects. But a tuple isn't hashable if it has mutable an immutable object. We'll get a type error instead. Tuples cannot be modified, ? Here we create a new tuple and replace it using augmented assignment. Or you could convert it to a list, modify it, and then convert it back to a tuple. Tuple use cases include when data should not change, for example, coordinates or fixed configurations, as dictionary keys or set elements, returning multiple values from a function, dictionaries. A dictionary is a mutable object that maps hashable keys to any data type. It contains comma-separated key value pairs, where the input is mapped to the output, enclosed in curly braces. Dictionaries became ordered in Python 3.7. Dictionaries are also known as a hash table, a map, a mapping, hash map, lookup tables, or associative arrays. A key is a unique immutable identifier, like a scalar singular value type or tuple if its objects are immutable, that links to a value. So you look up a key and you get a value. Values can be any type. Values are not indexed and there are no duplicate keys. There could be duplicate values, however. There are two ways to create a dictionary, the dict literal and the dict function. Wait. Let me back up to make sure you guys read that here. Okay. The dict function can handle iterables of key value pairs, keyword arguments, and zip objects. There are two ways to access values. The get method, which avoids a key error if no value is found. Keys can be hashed. Dictionary use cases include storing structured data like JSON-like objects, fast lookups, and counting occurrences like word as a key and count as a value. A set is an unordered collection of unique items of any immutable hashable type enclosed in curly braces. Elements are also referred to as keys. A set is like a list, except they're unordered. Sets do not record element position or order of insertion. They don't have duplicates, no sequence-like behavior like indexing or slicing. The set itself is mutable. We can add or remove items. But the keys must be immutable because they're turned into hashes. So very fast lookup compared to lists. Set use cases include storing unique objects, removing duplicates from sequences, membership testing, and performing math set operations to compare data structures in various ways. let me turn it here. Sorry, guys. Okay, so we're gonna, let's see. There's two ways to create a set, the set literal and the set function. Both can construct or convert sequences, iterators, and generators to a set or an empty set. There is no order. So if you want to create a new word, this is one way to do it. The usual case is to pass it a variable representing some data. We'll pass a tuple, and we get an unordered set with no duplicates. Best practice is to use a set function, and maybe use the set literal for making quick little sets from scratch. But it looks like a dictionary, which can be confusing. Let's pass it a dictionary. Only the keys were passed. Let's pass it a nested list. And we get a type error. Lists are not hashable. Strings. A string is an immutable sequence of Unicode characters enclosed in quotes. Each element is a singular character, a Unicode point. Okay. We can concatenate strings. The string function takes numbers, byte-like objects, and objects implementing the string dunder method, which includes most objects. So for example, the string function is a helper that looks to the string dunder method to say convert something into a string. Once we define a string, it cannot be modified because it's immutable. So in this case, we get a type error. Strings are hashable. All the more complex data structures discussed here have their own methods and functions. You can do a lot with string methods, including dunders. Here are the functions that apply to strings. Use cases include storing and manipulating text data, processing input and output, and using regex pattern matching. So I have an example here of inefficient versus efficient. Say we have 100,000 users in a list. To search for a name, you have to search item by item. If it's near the end, it's going to take longer. So on average, you have to search through 50,000 items to find a match. Oh, sorry. Here's the example. Okay. And with the set, the item is found instantly. So the set offers an incredibly massive efficiency gain. So when you're thinking about some data, its characteristics and behaviors and data structures, some questions you can ask are, will the data be changing? Do you want a mutable or immutable data structure? What data types will you be working with? Do the items need to maintain order? How will I handle duplicates? How will I look up, modify, or add or delete items? how big is the data? Does memory usage matter? As we've seen, Python's core data structures, lists, tuples, dictionaries, sets, and strings each have their strengths and best use cases. Whether you need ordered sequences, immutable collections, key value lookups, unique items, or string processing, data structures are the tools to manage data efficiently. The choice of data structure can make or break your program's performance, readability, scalability, and a simple switch from a list to a set or from a tuple to a dictionary can optimize speed, reduce memory use, or enhance code clarity. In addition to this table, there are many more specialized data types. What's a time when choosing the right or wrong data structure made a big difference for you? Do you have any tips about approaching data or any comments? Thank you.
I have just one horror story about using a dictionary as an input argument as a default value for the arguments. Bad idea.
Don't do that.
Any mutable.
Any, yeah,
Any
that
mutable.
applies to
Yeah,
any
a list as well.
Right.
Because the thing is that when you call the function the next time, it's not going to start with an empty argument. It's going to use the actual object you created before. So use it that way if you want caching, but my guess is that you don't.
It's going to stay there. You're going to mutate it, and it's going to be a side effect that you're not aware of.
That is a footnote.
Pass a none.
That's a none, yes.
Pass a none.
And then create an empty list or dictionary inside the function.
Yep. Cool.
Okay, that was fun, guys.
Thank you.
Thank you.
Okay, I'm gonna stop sharing here, I guess.
Well, that wraps up our meetup. Oh, that's my timer. That wraps up the meetup. Thank you for coming. I do want to thank our speakers for taking the time out of their day to put something together, and I want to thank Qualcomm and Neo4j for hosting us and for providing the pizza. And we'll see you next month. Stay tuned to the meetup for where it's going to be exactly, but I'm pretty sure it's going to be a building queue. The other one, not here.
Let's see. Live stream is probably not going to be happening. So
Yeah, there probably won't be a live stream next month. So, yep. Yeah. Anyway, cool. Thank you.
Thank you all.
All right. Awesome. So the problem, I don't know if this was the problem, but when I restarted OBS and plugged in my laptop, everything like all zero is might not, which it is.
Exactly.
Well, the bowl of zero is false.